This is my PHYS2211 Lab 5 video. Drop and shoot. Instruction that the purpose of this lab, based on the video that I got from YouTube from Harvard, is that they analyze the motion of the falling cue ball in order to determine not only the energy loss of the system, but the basic interactions of elastic collisions in general. Furthermore, we need to analyze the motion via tracker and the model of motion via glow script to show the motion of the collisions of the cue ball, specifically in the y direction. And furthermore, this lab is to further knowledge on collisions as well as to refresh one's mind on the properties of projectile motion and how to solve for variables in that case. Additionally, for some of the physics concepts that we utilize in this lab, we use the conservation of momentum for elastic collisions as shown right here with mass and velocity. Then we use the velocity and position update formula mainly for the glow script model in order to update the position and velocity of the model. And then Newton's second law, as an object will accelerate in the direction of the net force on the object, while the summation of forces from the surroundings on the object making said net force. And the only force at play in this case would be a force gravitational. And now let's move on to the tracker model showing said motion. The motion of the ball, as you can see, I put the axis at the floor, representing the floor of the ball as it bounces off, and I measured the accurate measurement between the contraption of the shooting ball mechanism versus the ground was measured to be 1.25, and now with the initial position of 0.284 and 1.256 in the y, we can see the motion of the ball as I plotted both the point masses right here, graphical representation of the time versus y and distance, which also could represent the x direction in terms of the shape, and as well as the graphical information over here versus the time and the x direction and the y distance, or x distance and y distance versus time. Now, for some of the data measurements and observations that we conclude, the mass of the given object was 10 kilograms, or the one that is bouncing away. The initial velocity, at least in the x and z direction, are 0. The gravitational constant in this case is 9.81, because Earth. Time before the first collision is 0.5 seconds, and the time of AR for the first collision is 0.033 seconds. Now, the position in this case, which is measured before, is 0.284 in the x and 1.256 y meters. Now, the calculated values, which I'll explain later, the velocity in the x is 2.06 meters per second, velocity before the y collision is 4.96 negative meters per second, and after the collision is 4.44 meters per second. And now the change in the energy system after the collision is negative 20.1. With the calculated values in mind, we can calculate these values versus the velocity in the next direction, which we can use the position in which the ball collides with the ground, as well as which is dt over v, and we take the initial velocity or initial position of the x and minus the final position of the x over the time before the first collision, being making the velocity 2.06 meters per second. Velocity in the y direction, which is the gravitational constant, so we need to use vf squared equals vi squared plus 2ad, which gives us negative 4.96 meters per second. Velocity in the y direction after the collision, we can use the top of the graph for that after the first collision in order to calculate the exiting velocity, using the same formula as before with y direction before the collision being 4.44 meters per second. Then energy loss in the system during the collision, we can use kinetic energy before and after the system to calculate said energy loss along with mass. Continuing on, we have some basic coding changes, which I use similar code from Lab 2 for the motion, in which we have t, delta t, gravitational constant j hat, as well as the calculation of f net, and the velocity update and position update formulas. Additional code that I added is that for when the ball hits the ground, it will reflect off of it using a negative 0.9 and to change the ball's velocity, because the energy loss was around, the energy conserved in the system is around 90%. And there's no drag force based on the shape and weight mass of the object. And the ball's system, the mass being 10, and the ball's new position and velocity are updated right here. Moving on to glow scope, we can see that we have the same visualization graph formation as Lab 2, and then the changes and similarities between the two, as shown before in the previous slide. Next, we can see that the gravitational force constant is going down here, as shown in the arrows of the lab visualization, as well as the graphical information of that and the plots of all the points shown right here. So we can analyze the motion of the cue ball that was launched as a constant acceleration, and it'll lose energy when interacting with the ground, and the momentum would transfer to the ground, converting that into energy types such as sound and heat. Furthermore, this demonstrates its Newton's second law, with the gravitational force of the cue ball has no force on the cue ball in the x direction. Overall, the lab allowed me to furthermore analyze and understand the momentum and elastic collisions and how that motion correlates through projectile motion. Furthermore, to further understanding of the system, we can analyze some of the questions that I asked myself, which is, does the energy realistically always stay conserved with elastic collisions? No. Obviously, the loss of energy of the system is elastically collides with an object always has a little loss of energy, at the very least, whether that be in thermal or sound energy, similar to how during the elastic collisions the cue ball made with the Earth, the energy wasn't consistent with the system as the ball wouldn't be nearly identical, yet opposite y velocities with the mass size of the Earth. Unlike complete inelastic collisions, which are more likely to occur, complete elastic collisions have almost an impossible chance of occurring. Finally, what would happen to the motion of the ball if the ball had a greater mass? What happened to the change in energy? Overall, the motion of the velocity of the object would not change before the first collision. After the first collision, the amount of energy lost would be greater if the object was the same, but would just a larger mass. Furthermore, this would be more likely due to the loss of energy due to the thermal and sound, with the force needed to rebound the object back off the Earth, causing the exiting velocity after the collision to be less than the exiting velocity of the normal system. Additionally, if the change in energy of the system would also increase, even if the exiting velocities would be the same, as if the mass increases with the same exiting velocities, it would proportionally increase the magnitude of the change in energy of the system as well. Thank you.